And today we'll start with the module 3 of the course, which is the first fundamental form. So in first fundamental form, so far we have covered modules 1 and 2, where we talked about introduction to curves, describe about various parametrization and everything, right? Parametrization and talk about some different types of curves, and also about nodes and links, which happen to be uh, very useful in studying structures such as DNA and all, right? And surfaces, we began with definition, talked about different types of surfaces, smooth maps, and how do we determine derivatives and tangents and normals as well, and what are level surfaces, what are certain special types of surfaces called quadric surfaces, which happen to be, say, surfaces um, like say the ellipsoidal surface, right? Just the boundary of the ellipsoid. So those surfaces are come under quadric surfaces. Then we have rule surfaces, where we have some sort of a generator uh, which can just translate over, or which seems to be uh, in a sense that we have some sort of a curve, and over which we have a line which just traverses the curve. And based on the different orientation we can form things like cylinder, even cone, and right. And then we have what we call as surfaces of revolution. So in surfaces of revolution, we talk about things called the profile. We have a profile curve which, when rotated about an axis, right? Then we generate things called the surfaces of revolution, and we touched a bit about compact surfaces, and briefly mentioned, briefly had a view of inverse function theorem. So today we'll start with first fundamental form, and we'll talk about the lengths of curves and surfaces, isometries of surfaces, the conformal mappings of surfaces, things what we call as the equiareal maps, which preserves area between two surfaces, right? Those maps which preserve area. Uh, then we'll just briefly mention about spherical geometry. So that is the goal for today's lecture. So it's going to be our lecture number 7, lecture number 8. Okay, so so far we have talked about surfaces and everything, surfaces and curves, but now we would like to also talk about some sort of a quantitative description about, say, quantitative description of surfaces. Like if you have any 2 points on a surface, just as an example, so you have this surface, right? And and of course it's 3D, so yeah. So we say this point and this point, right? Say P and Q, and the distance between these 2 points, we cannot directly just uh, join them by a line segment and calculate its length. No, that's not how. Because the thing is, we are allowed to move only on the surfaces, even when finding the distance between P and Q. So in that case, we will have to talk about how do we determine the distance between these 2 points while traversing along the or traversing on the surface itself. So there is where one example of what we call as the first fundamental form comes in, right? So we were talking about the first fundamental form. First fundamental form. So this is what we are going to talk about today, or discussing today, right? So first of all, uh, in the first fundamental form, so we will talk about lengths of curves on surfaces. on surfaces. Now this is the thing is, say we are only allowed to traverse on the surface. Then the distance, again, I'm at the cost of repeating myself. So we cannot directly go from point, I mean, we cannot just move from point P to Q by just connecting them via line, right? Just on, not by just traversing on the line segment, which just connects both these points. Rather, what we have to do is we will have to traverse, we'll have to walk, or say whatever, if you take driving or maybe anything, right? So, but it should be terrestrial, so to speak, right? So you will be moving on the surface and the distance gets incremental. I mean, you are moving, I mean, the distance keeps on increasing, right? I mean, the distance that we traverse as we proceed along the surface until we reach here, till we reach point Q. So the entire that the total incremental lengths gets summed up to give us the total length of a curve which joins P and Q. So as we recall, we had introduced something called as the arc length. Right? So we had talked about something called S, the arc length, right? S is equal to the norm of gamma dot and dt from T0 to T1. So if this is from T0 and this is the T1, this is the parameters, right? Parameter T varies from T0 to T1, then this will give us the total arc length. So maybe we'll have S total, we can say it. So which means that we are required to find, we need to determine the tangent vector. Right? And so once we determine a tangent vector, we take its norm, and then it will of course be a pointwise function. So we will keep on, I mean, tangent as a will vary with t, then take its norm and integrate over the interval for t. So we come to a definition here, formally establishing what we are trying to say. So the definition goes as, say, let p vector be a point of a surface S. Right? The first fundamental form of S. So this is surface S, say, at P associates to tangent vectors V vector, W vector is an element of TPS. And TPS is just the tangent plane to the surface at point P. So to every point, at every point P, we associate to tangent vectors V and W, the scalar, and the scalar is V vector, the inner product of gamma S, and this is equal to V dot W. So this is just the dot product. Looks very innocuous, right? Now, so here what we have is thus V vector, W vector, P vector, comma S is just a dot product. It's just dot product. However, there is a catch. They are restricted to tangent vectors at to S at P vector. So this is where so we define the dot product only for the tangent vectors which lie on the in the tangent plane to S at vector P. So of course, what all we have is that this is an inner product, right? Now, carrying on this idea for further. So this happens to be an inner product. There is an inner product. Okay. Now let's make it more formal. So suppose sigma vector uv, of course, is a surface patch of S, right? Then at any tangent vector uh, to S at point P, in the image of this surface patch sigma, and it can be expressed uniquely as a linear combination of sigma vector u and sigma vector p. And as we recall, both of them happen to be the tangent vector. I mean, they they happen to span the tangent plane at any point P to the surface S. Right? So here we define two maps which are very important even when we talk about the second fundamental form. So we have uh, we define the following maps. So the maps are du, and if it takes any vector v, then it gives us the tangent along, sorry, it gives us the component of that vector along sigma u. So this gives the component of v vector along sigma u, right? And the other, what we have is that dv So dv of v vector is equal to mu. And this will all happen only if we have v vector happens to be right. So this is how we define the vector v in terms of the basis vector sigma u and sigma v. And so as with similar to what the map du does to a vector v, we'll have dv also does work in a similar way. It's just that it gives the sigma v component of v vector. So these are the very essential maps, and we'll also deal with it in the second fundamental form when we discuss about the second fundamental form, right? And here for lambda and mu, both of which are real numbers. So now we can define something called as a and these maps are linear, so I'll just mention. Now let's try to expand the inner product operation that we had just talked some time back, which is just the angular brackets, right? So say gamma, sorry, the so this is also called as the bilinear, symmetric bilinear form. It's what we call as the symmetric bilinear form. So symmetric means that sigma a vector comma v vector is the same as sigma b vector comma a vector. And bilinear means linear in the first slot, linear in both the slots. Now, what do you mean by slots? So slot means the first argument and the second argument of the angular bracket. So it happens to be linear in both, right? So now we define what we have as the v comma v is equal to, then we'll just expand it, and I will write it as lambda sigma u plus mu sigma v, comma lambda sigma u. We're just repeating it. And now let's invoke what we call as the bilinear form. I mean, the properties of the symmetric bilinear form. First of all, let's try to expand along the first argument of this angular brackets, or the first argument of this inner product, right? So as per linearity, we can write it as lambda, which is just a scalar, and we can bring it out of the inner product, sigma u, comma lambda sigma u plus mu sigma v, plus, and the second argument mu again is a scalar. So I mean, it's a scalar, so we can bring it out of the inner product. And this will have sigma v, comma lambda sigma u plus mu sigma v. Then this will be, so we have invoked linearity, bilinearity on the first term. Now let's do so for the second term. So we have lambda. Then of course we'll have lambda into lambda squared. So it will be sigma u, comma sigma u, plus, then we have lambda into mu. So lambda mu. And we'll have sigma u, comma sigma v, right? And for the second case, what we have is plus, we have now let's expand it along the second slot, or the second argument of this inner product. So we'll have mu into lambda, and then sigma v, comma sigma u, plus, then we'll have mu into mu squared, then we have sigma v, comma sigma v. So here we have this term as well as this term. Then we invoke the the symmetricity of the of this bilinear form, right? So this is the same as sigma u, comma sigma v. It's equal to. So which means that we can write it in a more compact form as lambda squared sigma u plus 2 lambda mu sigma u sigma v plus mu squared sigma v sigma v. So there's it, right? Now, so which means that that's how we have defined the inner product of V with itself. So what we can do here is we will introduce the coefficients, or the metric coefficients is also true. It's also the other name for the terms that we are going to talk about. So you can introduce certain metric coefficients. And metric, as you recall, always implies measurement, right? Measurement of distance. Right. So we introduce these metric coefficients, which are E is equal to the inner product of sigma u with itself. This is just the norm of sigma u whole square. And F is equal to the inner product of sigma u and sigma v. And this is sigma u dot sigma v. Likewise, G is equal to sigma v comma sigma v is equal to just the norm of sigma v whole square. So using this abbreviated terms, we can rewrite our v comma v as e lambda squared plus e lambda squared plus 2f lambda mu plus g mu squared, right? And we can also write it down as, since we have lambda, we express it as du of v vector. So we can do it here as well. So we'll have du of v vector, that is lambda, and this whole squared, plus 2f. So lambda again is du of v vector. And then we also have mu, which is dv of v vector, plus g, and mu is the dv of v vector. Then we have whole square, right? So in literature, we in books, in literature, what will there are alternate expressions as well. So we also use the following expression as the first fundamental form. So it tells us E lambda squared plus 2 E du squared du dv plus g dv squared. And these are just differentials in u and v. Right. So these are differentials in u and v. And it's the first fundamental form. So you can say it. The following form is the first fundamental form of the surface patch. Sigma vector u comma v. And what we clearly see that E f g and these are the coefficients and the linear maps which are du dv, all depend on the choice of surface patch. However, the first fundamental form by itself only depends on, so this depends on the choice of surface patch or it depends not on the choice. It only depends on the here it depends on surface poise. It depends only on the surface and the point P. And we'll see it why is it the case later, right? So now if say we have gamma vector and it is a curve and it lies in the image of a surface patch sigma vector, then we have gamma vector t is equal to sigma vector, which is a function of ut comma vt. And of course, here the arguments of sigma are themselves functions of the parameter t. So this will be for some smooth functions which are u of t and v of t. Now then we can have gamma dot of t, which is like differentiating gamma with respect to t, is equal to, first we'll have parts, we'll use the chain rule. So we'll have partial sigma vector by u into du by dt plus partial sigma by v dot dv by dt. So this will be just sigma vector u and u dot plus sigma v dot v dot. So it's as if, and mind you that this we have gamma dot t. It is expressed in the basis vector of the tangent plane, TPS. So we can have uh, that we can say derive the inner product of gamma with itself to be E. Then all that we'll do is we'll have we'll just write it down, but it's of course not so necessary to repeat. But anyway, so you have sigma u vector plus. So this will be E u dot squared plus 2f u dot v dot plus g v dot squared, right? So this is the chain rule. And from here, what we can see is that the norm of gamma dot, as we recall, is the square root of its inner product with itself. And this will be equal to square root of E u dot squared so this we have. So of course, the length of the curve can be derived as, provided that we do not know the actual endpoint, so we can just have it as let's keep it without any limits on the integral. So we'll have this gamma dot dt, and this is equal to square root of E u dot square plus 2f u dot v dot plus g v dot squared. Then you have dt. So that is how we define something called as the length of a curve, right? And these curves are defined on the surface itself. So which means that they are constrained to the surface. Now let's do a few examples. So one of the few examples. So let's start with, say, example of a plane, of a, so to speak, a plane, right? So for a plane, what we have is the surface patch of a plane is sigma of the parameters u v is equal to some a vector plus So this A vector just lies on the plane. Schematically, it will be as if we have this plane here, and we have the origin of this as here, the coordinate system, and then any point we can. So this is any point on the plane. So this is just S, and this one we have as A vector, and any other point sigma. So it says sigma. So sigma minus A lies on the plane, isn't it? Because of which sigma minus A lies on the plane. So we'll have sigma minus A vector. So since it lies on a plane, and we say we have two basis functions which just define. So we have two basis functions, right? Say P and Q, P vector and Q vector, which happens to span this plane. So we can write A vector. I mean, the sigma minus A is equal to. So it means that now we have centered ourselves on the surface at here. Right? There's P vector and there's Q vector, and say both are unit vectors, right? So all we will have is U P vector plus V Q vector. So because of which you can just rewrite it as A vector plus U P vector plus V Q vector, where P and Q are orthonormal to each other. Orthonormal unit vectors, we can say. Right. So now, in order to define the first fundamental form, we require certain derivatives. So we have sigma u is equal to partial sigma partial u, and this gives us just P vector. And likewise, sigma v is equal to sigma by v, and this gives us the Q vector. Now, E is equal to sigma u dot sigma u, and this happens to be P dot P, and this will have just one because it's a unit normal vector, right? Likewise, or orthonormal unit vector, sorry. So F is equal to sigma V minus, sigma U dot sigma P. And this will have P dot Q. And as we recall, they are orthonormal, so the dot product of these two vectors is 0. And finally, we have G. So G is sigma V dot sigma V. And this again gives us Q dot Q, which is essentially 1. So the first fundamental form of plane is simply, we had defined the first fundamental form as this. So I'll just highlight it here. So we have E is 1, so we have just U squared, and F is 0, so we'll not have the product du dv, and then even G is 1, so we'll have just. So this is the first profile of a plane. Now let's talk about another example. This example now is of a sphere, or let's talk about the surface. We'll talk about sphere sometime later. So there is a surface of revolution. And as we recall, the surface of revolution, the patch is, so the way we define it is, so say we have this coordinate system, and our and this is XYZ. And we have a profile plane, profile curve, which lies in XZ plane, right? So there is a profile curve along which U is varying. So U goes along this. And then when we revolve it, so we revolve it in this fashion. So this revolving, so we start with V is equal to 0 from the profile, from the intersection of the profile curve with the y-axis, and then just keep on incrementing V. So V goes this way, right? So the profile plane, the expression is f of u, comma, and there is no y component is 0. The y coordinate of this profile plane is profile curve is 0. So you have 0, and then you have g of u. Once you rotate it about this z-axis, then you have this surface of revolution. The expression is given as f of u, as usual, into cosine v, comma, f of u, then sine v, comma, g of u. Now what we can clearly see that at v is equal to 0, cosine v is 1 and sine v is 0, because of which we are able to automatically get the profile curve. Fine. So, and we are also given that the profile curve is unit speed. So which means that so the profile curve in the unit speed implies that we have f dot squared plus g dot squared is equal to 1, right? Okay. And now we can construct the necessary requirements for to determine the first fundamental form. So sigma u is given as partial sigma partial u, and we will have, of course, what we are doing here is we are denoting d by du as dot, right? So this one will be equal to f dot cosine v, comma, f dot sine v, and then g dot. Now sigma v is equal to partial sigma partial v, and this gives us minus f sine v, f cosine v, 0. Right? Now let's find the metric coefficients. So E is equal to sigma u dot sigma u, and we have f dot squared cosine square v plus f dot squared sine square v plus g dot squared. So of course f dot squared cosine square v plus sine is 1. So f dot squared plus z dot squared, and then we learned that this is also equal to 1. So E is 1. What about f? So f is equal to sigma u dot sigma v, and this gives us, let's do it component by component. So minus f into f dot sine v cosine v, right? Then we have plus f into f dot sine v cosine v. So they just cancel out identically. So we have 0. And how about g? So g is given as sigma v dot sigma v, and all that we have here is f squared sine square v plus cosine square v, and this gives us f squared. So the first fundamental form is 1 dot du squared plus no f, so there is no cross term. And then we have plus f squared dv squared. And of course, we'll just, the argument of f is u. And then we have dv squared. Fine. Now let's talk, there will consider one more example. And this time it's going to be that of a cylinder. And here we consider a generalized cylinder whose surface patch is defined as sigma uv is equal to gamma vector u plus v a vector. And as you recall, gamma u is this here, right? So there is some curve and we are taking to be closed curve. And then we have lines which are parallel to a vector. So this is a vector and this was gamma vector u, and this u is the u varies along the curve. And what we have is parallel to a vector, we'll construct lines on this. And it will be, of course, infinity of lines. There is a continuum of lines. So v varies along this at every point and at u. At every u, you will have one such straight line, which is parallel to a vector, and that straight line will be parametrized parametrized using v. Right. So this is how we construct a cylinder. So we'll say we have prescribed certain end limits for gamma. So because of which we'll have a nice looking. So it's as if it will be a replica of this. So this is how you have you'll have a cylinder like this, right? Okay. So sigma u vector is equal to gamma dot, and just gamma dot because v and a both are independent of u, and sigma v vector is equal to a vector, which is a constant vector, and a vector is constant. So which means that sigma u dot sigma u is equal to gamma dot, and mind you that gamma u is a unit speed curve. So gamma dot gamma, this is equal to gamma dot norm square, and this as we recall is just 1 squared, right? Since gamma, and then sigma u, this is E, and F is equal to sigma u dot sigma v. So we have gamma dot a vector, and it may so it so happens that a vector is perpendicular to this curve, to this gamma u vector, right? So which means that the plane which is in which this gamma u is contained is perpendicular to a vector. So this gamma dot a happens to be 0, since gamma vector lies in a plane perpendicular to a vector, right? And then we have G is equal to sigma v dot sigma v. This is just a dot a, and even this a happens to be a constant, and it is a unit vector. So it's essentially a constant unit vector. So this is also equal to 1. So the first fundamental form that we get here is, so the first fundamental form of cylinder is, so you have d squared, du squared plus f is 0. So, and g is again 1. So we'll have, and this is as that for a plane. So So what we see is there has to be some explanation for why it happens. So the answer goes to the fact that uh, using a plane, we can roll it up into a cylinder, right? So which means that there is no stretching, so to speak, and that makes the lengths of the curves equal in both the for any curve in the plane, and if when we roll the plane into a cylinder, that length of the curve remains as it is, and that uh, gives us the right that reveals the the same fundamental form for the cylinder, I mean, as well. Okay. So now we'll begin with what we call as the isometry of surfaces. Isometries of surfaces, right? So here we'll have lots of definitions. Now, what do we mean by isometry? So isometry is mapping which preserve the lengths of curves. So that's what it happens to be. So as I mentioned that given a plane, we can roll it up into a cylinder, and if we draw any line on a plane, on a line segment of the plane, that after rolling it to the cylinder, of course, it becomes some sort of a curve. Then the length of that the curve in the cylinder will be remain the same as that of the line segment in the plane. And there is where, so what we can clearly say that rolling of a flat surface of a plane surface into a cylinder preserves I mean has this preserves the length of the curves, and which means that the mapping which takes us from a plane to a cylinder happens to be isometry, right? Okay, and we cannot. There is one more thing that we cannot say uh, say roll a paper into a sphere without introducing uh, say some cuts or without uh, having some discontinuous deformations, right? So because then we cannot get a sphere from a plane. So which means that the mapping which takes us from a plane to a sphere, of course, it does not exist in terms of continuous mappings. But what it does is that uh, they do not that mapping is not an isometry, right? And then we won't have even the same fundamental form. And as we recall here, even surface of revolution is uh, s- sphere is also a surface of revolution. And we can see that because of the fact that f square of u. So the first term is the same, but this f square of u, and unless it's one, and it's never going to be one for a sphere, because of this they don't have the first fundamental form, and therefore they are not isometric. Okay, so now let's talk about these definitions here. So we have this definition. It says that if S1 and S2 are surfaces, a smooth map F such that S1 to S2 is called local isometry if it takes any curve in S1 to a curve of the same length in S2. So it means that if a local isometry F such that S1 to S2 exists. If such mapping exists, we say that S1 and S2 are locally isometric. So the thing to note here is that, so of course, say we have a surface, just so there's S1 and there's S2. So the mapping of S, this F smooth map, which takes this from here to here, if it preserves the length, which means that any curve from here to here, say this curve, and even after applying the map F, if it's still so if they remain the same, the length of both the curves, which then it implies that F is a local isometry. Right? And we have certain extensions here that say every local isometry is a local diffeomorphism. And the local isometry that is a diffeomorphism is called an isometry. And of course, the properties are that the composite of local isometries and is a local isometry, and then point two is that the inverse of an isometry is also an isometry. So the idea goes that mathematically, say, let F from S1 to S2 be a smooth map and let P vector be an element of the surface S1. Then for any two vectors VW which lie in the tangent at P to surface S1, define we have this F star VW vector P is equal to, so this takes us the first fundamental form on the tangent, this one on the tangent plane is equal to the differential of dp comma so derivative of f at p along the direction W. And this is after the, so this is in surface 1 and this is in surface 2. Right? So again, F star dot dot, this is also a symmetric bilinear form on TP S1. So there we have the symmetricity. It's obvious, of course, and then it's also linear in that sense, right? Okay, so let's have a theorem. This theorem talks about this, the smoothness and the conditions for the local isometry. So we have a smooth map F such that S1 to S2 is a local isometry if and only if the symmetric bilinear forms dot dot P and this bilinear form on the on TP1, TPS1, and F star of the differential part as well, P vector on TPS1 are equal for all P vector is an element of S1. So this is how we construct right for the isometry part, right? Let's just give a brief proof of this. So proof is that if gamma vector 1 is a surface on S1, then the length of the part of gamma 1 with endpoints gamma 1 T naught, gamma 1 T1 is T naught to T1. We have gamma 1 dot, gamma 1 dot, the square root of this dt. So that is the length, right, of the curve on S1 for the n limits on the of the curve, right? Now say the length of the same curve, the length of the corresponding part of the curve after applying the smooth map, right? P of the curve, which is of course gamma 2, and it's obtained by the composition of F and gamma 1 vector. And this is on S2. Now this gives us T0 to, sorry, T1 to T0 or T0 to T1. And then we have the same formula, the square root of this into dt. And now we can So gamma 2 vector, this will be a differential on like we will have d of f gamma 1 dot comma right, and then d of f gamma 1 dot. So this is the differential, the square root of this dt, and this will be equal to t naught to t1. And then the f star gamma 1 dot comma gamma 1 dot half of this dt. So if it so happens that both the symmetric bilinear forms like this, if this and this two are equal, then say if uh, say if t naught t1 and then gamma 1 dot comma gamma 1 dot, if square root of this, if it is equal to t naught t naught to t1 of f star gamma 1 dot gamma 1 dot, if they are equal, then this implies that, of course, it implies isometry, and gamma 1 dot is equal to f star of gamma 1 dot comma gamma 1 dot. So this is the one part of the proof, like if the if part. For the only if part, like we need to go the reverse. So here conversely, what happens is, suppose oh, say if these two integrals are the same, right? This one and this, if they are the same, then of course this holds. Just remove it for now. Of course this holds, right? The integrands has to be the same. Now, since any tangent vector v to s1 is the tangent vector, right? So tangent vector v to s1 is the same as the tangent vector of a curve on s1. So it means that it implies that v dot v comma v is equal to f star. And this is for all v, since v vector belongs to the tangent plane of s1, right? So and since this and f star are bilinear forms, are symmetric bilinear forms, then it implies that it implies from this here, from this condition, that this is equal to. So which means that we first started with saying that, okay, we want the length of the some part of a curve on S1 after mapping it to to the S2 surface. We're looking at the same corresponding part of the curve and then determine the lengths. And if the lengths are equal, then of course it's a isometry. On the other hand, now our goal is also to prove that this should be the only case. So in that, for the integral to be valid always, we had that the integrand must be the same. Integrand must be equal, right? Now, we also found that any tangent vector v to S1, it has to uh, it will always be a tangent vector of some curve to the surface S. Then, which means that we can write for a generic tangent vector v, we'll have v comma v is equal to f star v comma v. And since they are also symmetric bilinear form, and then we use the fact that that this equality holds for all v. So which means that this for isometry, the uh, both these symmetric bilinear forms must also be equal always, right? Okay. So then eventually what we have is thus F is a local isometry if and only if dp of fv vector comma dp of fv vector fw vector at fp means after mapping, this will be the same as v comma w at p vector, and this should hold, for all p vector is an element of S1, and for all v vector w vector is an element of dps1. Right. So which means that this dp, this differential here dp of f, it maps from the tangent plane of at p of S1 to the tangent plane at of course at f of p vector on S2. So this is the linear map and it is an isometry. Right. So it implies that it preserves lengths. Right. Okay. So one corollary, and then we'll move ahead to talking about the conformal mappings, right? Okay. So the corollary, uh, which states that a local diffeomorphism f from f1 S1 to S2 is a local isometry if and only if for any surface paths sigma 1 vector of S1, the patches sigma 1 and the composite of F and sigma 1, and these are the patches of S1 and S2 respectively. And both of them have the same fundamental form, the same first fundamental form. right? And of course, we'll not prove it here. Now we come to the conformal mappings. That is our next topic of study for today. So far we have been discussing about how to determine lengths of curves on surfaces. Now we would also want to know the angle between say two curves at any point P, right, where they happen to intersect. So suppose that we have suppose two curves, gamma 1 and gamma 2, on a surface S, and let them intersect at a point P vector. Then the angle theta of intersection of gamma vector and gamma uh, 1 and gamma 2 at P vector. And this is defined as the angle between the tangents tangent vectors gamma dot and gamma 1 and then gamma 2 dot. And both of are evaluated at t is equal to t1 t01 and t is equal to t02 respectively. Right. So we know about the dot product dot form. I mean this one, right? That we have say if there is an angle theta between two vectors which happen to intersect, then it is given as their dot product. So gamma 1 dot, gamma 2 dot, divide by the product of their norms. So gamma 1 dot, norm of this, and gamma 2, norm of this. And we can, of course, use that in the inner product expression. We'll have gamma 1 dot, gamma 2 dot, divided by gamma 1 dot, gamma 1 dot, square root, and then we have gamma 2 dot. Okay, so the idea goes that you have, say, in the parametric space, which is UV. So this is how so this say is given by U1 comma V1, and this one is U2 comma V2. So they intersect here, and the image of the surface patch gives us this. And say we have this and this. So this one is our gamma 1 vector, and this is our gamma 2 vector. Right, and this is point P. So the angle at this is of the intersection is just the angle between tangents here. So this is the theta, and this is how we derive the expression for the theta. Now what we would like to do is that we want it to be in terms of the expression of the angle between at the point of intersection to be in terms of the surface patch. So what we do is, say we have uh, uh, let gamma 1 vector and gamma 2 vector lie in a surface patch, right? Lie in a surface patch of S. Surface patch sigma of S. And so that what we have here is that gamma vector of T is equal to sigma vector UT comma VT, right? And gamma 2 vector, and this is going to be sigma U2T V2T, right? And of course, these are all for smooth functions. For some smooth functions, UV, U1V, U1, V1, U2, V2, right? Now, since we have the first fundamental form, if say E du squared plus 2F du dV plus G dV squared and is the first fundamental form, of sigma vector, then what we have is that cosine of theta will just be in terms of the first fundamental form, and we can write it down as E U1 dot and then U2 dot plus F, then you have U1 dot V1 dot plus U2 dot okay, so yeah, 2 dot V2 dot. There is some sort of a cross coupling, right? So rather you can just call it as U1 dot and then V2 dot plus U2 dot V1 dot, okay? And then plus we have G of V1 dot and V2 dot. This divided by their individual square root of the first fundamental form. So U1 square plus U1 dot square plus 2F U1 U1 V1 dot plus G V1 dot squared, the square root of this, and here you have U2 dot squared plus 2F U2 dot V2 dot plus G V2 dot square and square root. So this is what we have here, right? And I'll just be giving a few definitions before we move on to talk about that equiareal inequalities. So equiareal maps are. Then the definition says that if S1 and S2 are surfaces, conformal map F, which maps from S1 to S2, is a local diffeomorphism such that if gamma 1 vector and gamma 2 vector are any two curves on S1 that intersect at some point P vector, which is an element on S1 of S1. And if gamma 1 tilde and gamma 2 tilde are their images under F, then what happens that the angle of intersection of gamma 1 vector and gamma 1 vector tilde or actually it should be gamma 2 is at P vector is equivalent or is equal, sorry, it's if the angle of intersection of gamma 1 and gamma 2 at P is equal to the angle of intersection of gamma 1 tilde and 2 tilde at FP vector. So this is what it is, right? In short, F is conformal. The map F is conformal if and only if it preserves angles. Right? So let's talk about equiareal maps today. So what is an equiareal map, right? So consider that we have, suppose that sigma vector is a patch from U to R cubed. Is a surface patch, right? It maps from a parametric space U to R3 is a surface patch on surface S. Then the image, right? Then what happens is the image of sigma is covered by two families of parameter space of parameter curves. And these are obtained by setting U is equal to constant and V is equal to constant respectively. right? So what happens is we have this parametric space here, right? And we fix this point as u naught comma v naught, and this is u and v axis, and of course 0. And this will be u naught plus du v naught, and this one will be u naught plus du comma v naught plus dv, and this here, this corner is u naught comma v naught plus dv, right? So this when we map to surface, right? So initially say this is the surface. So let's say this is our point and this is our mapping. So this gets mapped to here. So this will be our sigma vector u naught comma v naught, and likewise. So this length, the infinitesimal length will be sigma u du, and along this we'll have sigma vector v and dv, right? So this is how we are mapping it to this, right? Along this will be u is equal to constant line, so u is equal to constant, and this is v is equal to constant line. So it's locally, it's as if we have a rectangle in the infinitesimal imagination. That's how we can call it. So this happens to be some sort of a small rectangle, right? So or small parallelogram. Then what we'll have is the area of this. So the area of the parallelogram with sides say vector u du and sigma vector v dv is approximately with sides on the surface S1, sorry, S, this is surface S, right? So this is given by the norm of the cross product of this cross sigma v. I'll just call it du since we're already assuming to be infinitesimal, and dv, right? And this comes out to be just sigma u cross. Right? So the definition goes as the area A sigma of r of the part sigma r of a surface. So say we have this as the sigma vector, the part of r, right? And we have certain region defined, right? Even in this case, let we define some region. So this say let it be this region over which we want to integrate, or which this was the small, highly exaggerated part for which we wanted this, right? So the part sigma r of a surface patch sigma vector from u to r cubed corresponding to a region. So this region is R in U space to a region R, which is a proper improper subset of U, and it is given as a sigma of R. This is equal to the integral over R, then the cross product of sigma U and sigma V integrate over du d. Right? Uh, Now what happens is we have a proposition here. It says that sigma u cross sigma v vector, and we can easily derive it to Eg minus f square root, where E du square plus the E du square 2f du dv plus g dv square is the first fundamental form, right? So now for a regular surface, this term Eg minus f squared is always going to be greater than 0. So therefore, we'll have the definite area as a sigma of r in terms of this coefficients, metric coefficient we have square root of Eg minus f squared integrate over du dv. And a further proposition says that so there's another proposition which states that the area of a surface patch is unchanged by parameterization. Of course, this can be proved, but we are not going to prove it here. Parameterization. Right? And for the condition for uh, for this can be put in terms of a theorem. It says that a local diffeomorphism f from sigma s1 to s2 is equiareal if and only if for any surface patch sigma vector u comma v on S1, the first fundamental forms E1 du square plus 2f1 du dv plus g1 dv squared and E2 du square plus 2f2 du dv plus g2 dv squared of the patches. So these are the first fundamental forms of the patches. Sigma vector on S1 and FO sigma on S2 satisfy E1 G1 minus F1 squared is equal to, if these happen to be the same, then it is a equiareal surface, right? Or equiareal maps, right? Of course, we had this spherical geometry. I'll just we'll just uh, make a passing remark on this without going further here. So since this topic requires a lecture of its own. So the idea is like we have been talking about so far about Euclidean geometry, but then we also have things called spherical geometry where uh, we move along the or we determine all this perform calculus on the sphere itself, right? And this subject has been of great interest so far in since quite ancient times due to the interest in astronomy, right? So here uh, we always have to we have a sphere and then we talk about the great circles on it and all that. It's typically in geography we call it latitudes and longitudes, isn't it? So that's how, and what are the conditions on it, and what is the shortest length of it for a curve joining any 2 points. Say we have a sphere here, and then we have sorry, we have some sort of so we have this whole. So say we have any 2 points on this. So this led to point P and this led point Q. So we want to find a distance which is the minimum distance between those when we move along the sphere itself. So we talk about things like this in spherical geometry. And since it's not very relevant right now to what we would like to further pursue in this course, we'll just give this passing remark here, and I'll just close the discussion for this here. Okay, so in the next session, we will talk about the second fundamental form, and yeah, so that's what it is. Okay.